Thanks APS Mars Meeting Committee for inviting me to attend this world-renowned Mars Meeting 2022 as a focus session speaker. I'm delighted to see you here, scientific community, and honored to be in front of you and present my research on perovskite material. The title of my presentation is A Comparative Study of Mechanical Stability, Electronic, Optical, and Photocatalytic Property of Cesium-lead halide by DFT calculations for optoelectronic applications. Before starting my presentation, I would like to introduce my country first. I am from Bangladesh, recently declared as a developing country of South Asia. It is surrounded by India by all sides except south. Here we can see the geographical map of Bangladesh in our globe. We have world's largest mangrove forest, Sundarban, a very special species, Royal Bengal tiger in it, the world's largest sea beach, the Cox's Bazar, and many more archaeological and historical places such as 60 Dome Mosque, Asan Manzil, Buddhist Bihar, etc. My institution, Begum Rokeya University, Rangpur, has started its journey in 2008, whereas my department started so in 2010. It is a part of my academic buildings, my department interior, and our material science research lab, where I am working as a part of research team. Here on the southeast side, you can see the photo of my research team attended on an international conference 2020, Dhaka, Bangladesh. I hope you can understand the hardship faced by a newborn department of an institution of a developing country for lacks of resources. Although there is no mandatory to do research work in the undergrad level, I have started my research journey with very limited resources and lab facilities in 2019 as the first UG student in my department. And this was my first research project as a co-author, for which I was awarded for the Best Poster Presentation Award in 2019 in ICPSDT 2019. It was also based on a perovskite material. Come to our main points of concern. I am going to discuss about the intro part of the material, why I have chosen the cubic phase over the other phases of the cesium-lead halide, theoretical approach to do this analysis based on structural property, mechanical stability, electronic, optical, and photocatalytic property, and finally I will discuss the conclusion of my presentation. Cesium-lead halide exists in three phases such as cubic, tetragonal, and orthorhombic, recorded by many researchers, and we have chosen the cubic perovskites of a space group PM3M of number 221. Let's see why we have chosen the cubic phases. We have chosen the cubic phases over the rest of the two phases as we have an intention to study the pressure dependent properties also. The temperature and pressure are directly proportional. The cubic phases are suitable for higher pressure and temperature application. So we have chosen the cubic lead halide perovskites, where tetragonal is suitable for room temperature and orthorhombic is suitable for low temperature application. Halide exchange and mixing can ensure more suitable property tuning of cesium-lead halide for quantum dot applications due to their high carrier transportability, reliable optoelectronic and photovoltaic properties, enormous photoluminescence, quantum yield, optomagnetic photonic lensing, display application, single and multiple pumping based on laser devices. Let's have a look on the theoretical approach. My research is based on computer simulation and investigating some important properties of perovskites. Here I have employed Materials Studio simulation software. I simulated cesium-lead chloride with cutoff energy 520 electron volt and K point set were 666. I carried out these calculations using CsPbX code. The first principal calculation were carried out using ultrasoft as well as norm conserving pseudopotential method, where I selected GGA, generalized gradient approximation, for calculating ion-electron exchange correlation. After finding the optimized structure, the characterization based on mechanical property, electronic property, optical properties are investigated. Cubic structure of cesium-lead chloride, bromide, and iodide are depicted on figures A, B, C respectively. where halides are face-centered atoms, lead takes place in the position of body-centered atom, and cesium is the corner atom of the cubic bug. Table 1 shows the collection of some values regarding lattice parameters, volume, band gap of the perovskites. As we have chosen cesium lead chloride first and decided to replace halogen for tuning the properties, both norm conserving and ultra-soft pseudopotential methods are implemented to get a reliable result. The table shows the theoretical results have a good agreement with experimental one for ultra-soft pseudopotential only for lattice parameters and mechanical properties. Optical properties are more closer with experimental values for norm conserving pseudopotentials. With the insertion of bromide and iodide in the place of chloride atom, the lattice parameters increases due to comparative larger ionic radii of bromide and iodide atom. But the opposite trend is observed for the band gap values. Now let's have a look on the pressure independent and dependent mechanical properties. All the mechanical properties are calculated implicitly and explicitly by these three elastic tensors C11, C12, C44 shown in figure 4a. Mechanical stabilities are confirmed by Born criteria. All the materials exhibit more resistance to longitudinal deformation over shape deformation due to the highest value of C11 and the lowest value of C44. The pressure responses of CsPbX are depicted in figure 5. The comparative dataset of B, G, E and B over G Pau's ratio confirms the highest ductility of cesium lead bromide, whereas cesium lead iodide has the lowest one. The universal anisotropic factors and melting point temperatures are added with the supplementary files of the presentation material. From figures A, the threshold applied pressure above which cesium lead chloride and bromide lost the mechanical stability are 20 and 25 gigapascals, where it is 75 gigapascal for cesium lead iodide. Young's modulus increases with pressure for all of them, but the nature of increment is different for cesium lead iodide. The zigzag curve of C44 gives the information about pressure dependent phase transition of cesium lead iodide. It has highest damage tolerance, but the highest mechanicability index is observed for cesium lead bromide. This is the comparative energy band diagram of norm conserving and ultra soft pseudopotential method. Here you can see in the table the band gap value is so much closer to the experimental value for norm conserving pseudopotential. So we have carried out our optical properties and electronic property analysis in terms of norm conserving pseudopotential method. Electronic properties are studied as a form of energy band diagram with corresponding density of states for different atomic contribution. The attractive potential between conduction band and valence band increases due to the halide replacement. The energy band gap decreases with bromide and iodide insertion significantly. The major contribution of the formation of valence band are changed due to the contribution of p orbital of halogen atoms. It is clear that lead and halogen atoms have major contribution in valence band and conduction band to reduce the band gap. The valence band and conduction band of cesium lead chloride are due to dp hybridization. The valence band of cesium lead bromide and cesium lead iodide are for dp hybridization, and the conduction band of cesium lead bromide and cesium lead iodide was for sp hybridization. The higher carrier mobility is confirmed by the higher energy band curvature of cesium lead chloride. Optical responses in terms of dielectric functions, absorption coefficient, conductivity and reflectivity of cesium lead halide has been shown in figure 9. Due to the higher band gap value, the exciton production is less for cesium lead chloride and it increases for bromide and chloride replacement. The order of optical band gap of these three perovskites are reconfirmed by absorption spectra. It is highest for cesium lead chloride and the lowest for cesium lead iodide. The highest optical absorption and dielectric functions is observed for cesium lead iodide indicated by the blue lines. The reflectivity order follows the opposite trend for low energy region and ultraviolet region. Conductivity increases at high energy side for cesium lead chloride. Cesium lead chloride, bromide and iodide are suitable for green, orange and red emission respectively. An idealization of photocatalytic activity arises from the narrow bandgap, low recombination rate with long carrier life and proper redox potential. The redox ability for visible light exposure can be calculated theoretically by aligning the conduction band minima and valence band maxima compared to the water reduction oxidation potential level. Figure 10 has been plotted from these values, which implies that cesium lead chloride is suitable for oxygen production, which can be used as nanoparticle to refining water and to increase the oxygen level of polluted water of rivers. Cesium lead iodide is potential candidate for hydrogen production, which can play an important role in hydrogen fuel-based power plants. Cesium lead bromide is a best performer for photocatalytic process in visible region due to nearly equal effectiveness of oxidation and reduction processes. I'd like to conclude the comparative study with the following points. Cesium lead bromide is thermally and mechanically more stable than the rest of perovskites. The mechanical stability losses at 25 and 30 gigapascals for cesium lead chloride, cesium lead bromide, but for cesium lead iodide it is lost at 80 gigapascal. Direct bandgap observed for cesium lead halide with a value of 2.385, 2.061 and 1.784 electron volt respectively. From the curvature nature of bandgap, it is evident that the higher hole mobility possesses for cesium lead iodide perovskite rather than that of cesium lead chloride. Cesium lead chloride, bromide and iodide are suitable for green, orange and red emissions respectively. Theoretical photocatalytic calculation demonstrated that cesium lead iodide is best performer for hydrogen production. Cesium lead bromide is most stable photocatalyzed due to the balancing position of oxidation and reduction potential, but cesium lead chloride would be a better candidate for hydrogen production. Here you can see the author's contribution, and these are the references. Thank you for your kind attention and precious time.